Bob is out today, so I thought I would just go over some field testing that I did yesterday. What you see here is an after the run artifact showing the path that I traveled and the fix quality during that path. So it was a simple test of the pure pursuit controller on my Ackerman Cub Cadet lawnmower. It comes down here, makes a sweeping right hand turn. These blue marks indicate the loss of RTK fix, which is going to be an ongoing discussion and analysis. But instead of just looking at the map, this is the actual tractor. I've got the sound turned off here so you don't hear the background noise. What's important to me is that the steering is pretty quiet, and by quiet I mean it's not doing a bunch of left and right turning in order to maintain the track. This is my DIY remote control. The switch being in the down position indicates that it's in what I call auto mode, which means the pure pursuit controller is controlling the steering as well as the speed. LED lights indicate NRF radio strength, RTK fix, and this is the mode. I don't have a programmed use of this button yet. Now when I switch back into manual mode, this potentiometer controls the transmission linear actuator, and it's slightly to the right, which means it's going to apply a little bit of forward motion. This potentiometer controls the steering, which means the steering would turn left, but since it's under auto mode, the pure pursuit controller has control of the steering. The reason it's paused is because it's lost RTK fix. We're probably at that point right now. It's going to go down here and make a sweeping right turn. That argy-bargy looking thing on the back is a bungee cord to hold the cutting blade up. The cutting blade is not running. I just didn't want that banging around on the ground. Again, a slight pause for RTK fix to get to collect itself. I have wheel odometry equipment on this, but I've not integrated that into the pure pursuit controller, so at the moment if I lose fix I just simply pause for a second. So we're on our way back now. We've completed the turn and we're heading in this direction. It paused. I think that might be the last. A couple of quick pauses. Once I integrate the wheel odometry data, I've got a number of different solutions if I lose RTK fix. First is to try to figure out why I'm doing that. I've tracked the number of satellites and it's certainly 12 and I'm in open area. So again, just more testing. This is the first serious test of using the pure pursuit controller. I'll also pause the video and talk briefly. This collection of components here make up my base station, RTK base station, solar panel, Starlink, Mini in order to get Wi-Fi. Underneath this box is a Wi-Fi router, which is broadcasting an SSID across the yard. There's a GPS antenna down in the grass. I did a 5-minute survey in order to figure out the position. Here inside this box is a 35 amp battery, an RPi-3, an ESP32, a solar charge controller, and the GPS that's picking up this GPS satellite. I haven't mentioned it before. I've mentioned it in other videos, but not on this one. There's a heading antenna and a base link antenna feeding to F9P Ardu Simple U-Blocks GPS units. On this board on the other side is, I've covered it before, but an RPi-5 and a Teen Z4 in addition to the GPS units. So here it's going to declare mission complete, it puts it in neutral because there's an incline. It's rolling back a little bit. I'm going to put it in manual, and it's going to pull forward a little bit, and the wheels are going to turn a little bit left. They're going into manual, pulls forward just a smidgen, and the wheels start turning left until I drive it back to where I want it to go. So that was, in my mind, a successful test of this Pure Pursuit controller, which is in my GitHub repository. The mission, this is an example of what a mission file looks like. Lat long position, heading in radians, look ahead distance, which the Pure Pursuit controller uses, and the speed I want. That speed was about 1 meter a second. This was just from a previous test. Speaking of tests, I ran a number of speed tests in order to get these settings. Basically on the left is what speed would be delivered. On the right is the PWM signal sent to the linear actuator that is connected to the hydrostatic transmission. This is used by the Teensy, which is the low-level controller, but the speed value on the left is sent through this mission statement. And these are all of the linear actuator settings for the hydrostatic transmission. If I'm in manual mode, I get 5 forward settings, 4 reverse settings, and this 2836 happens to be neutral. These are some other missions that I ran. This was a completely manual run. I was trying to figure out what's the radius on a hard right and a hard left for the tractor, and I'll adjust that over time. I still have some room, I think, to adjust this set point lower, which would lower this fitted radius. This is pretty firm. I think this is a physically can't go any further left turn on the tractor, but on this one I think I've still got some buffer I've not used up. So I gathered this data about what does a hard left and hard right look like, and then I programmed a mission again to come out, make a sweeping right turn, but in between to make a hard left and hard right programmatically, and this was the result. So it was able to deliver a 1.2 and a 2 meter radius circle. This is a result of, well, it's the same path, but showing what was the target path and the actual path in order to calculate what's referred to as the cross-track error, or CTE. That particular point right there, it was 0.13 meters off the path, which, what is that, 5 inches or so? So over time I need to work on improving that. There's some analysis overall and the percentage of time. What I'll show you is, if this is out in my GitHub repository, and so if I download that and open it, I can zoom in. What I wanted to show you is this sweeping right turn. It's consistently has a cross-track error of close to 0.3 meters, and it is definitely a little bit better on the straights. So again, pretty happy with the steering control and the Pure Pursuit controller, but obviously room for improvement. And speaking of improvement, this is a write-up on I've got a gazillion next steps and action items, but this is just a markup file to document so I don't forget. What can I do to improve my analysis and data collection in the Pure Pursuit controller? Because this controller serves two functions. It controls the actual steering, but it also logs a whole bunch of data and puts it in a CSV file, and I want to improve that in order to capture more data to be able to further improve the steering. Let's see, other takeaways from field testing. This was just a graph of controlling the speed and setting the speed and monitoring was it able to deliver, and that's why I made the changes to these tables in order to better match the desired speed with the actual speed. One of the challenges I had to overcome is white rust. I need to get a watertight, airtight enclosure for my electronics and then put a Gore valve on there that doesn't let moisture in, because right now I've got white rust or corrosion going on and needed to get some of this special WD-40 in order to clean that off. And I think that's yeah, so all in all, pretty pleased with the path and the control, and obviously there's improvement, but things are working out pretty well right now. Thanks, have a great day.